Welcome to this explainer. Today, we're taking those static, two-dimensional structures you see in organic chemistry and bringing them to life. We're going to transform them into a dynamic, microscopic game of tug-of-war for protons and electrons. We're decoding the absolute fundamental rules of acidity and basicity. By the time we're done here, you'll be able to look at these structures and predict exactly how they're going to behave.
Here is our roadmap for today. We've got 5 stops: the acid-base rulebook, measuring strength, acid strength factors, organic bases, and finally, base strength factors. Let's just jump right in.
Take a look at morphine. We all know it as a powerful painkiller, but chemically, it's a total chameleon. Depending on the environment, it can actually play both sides. It has specific oxygen-hydrogen bonds that make it act like an acid, ready to give up protons. But it also has nitrogen atoms with lone pairs of electrons that make it act like a base, ready to accept them. It's fascinating. But to really understand a molecule like this, we need to know the rules of the game.
Section 1, the acid-base rulebook. Let's define our key players.
So chemists generally use 2 main definitions here. The Bronsted-Lowry definition is all about the proton, specifically donating or accepting a hydrogen ion. A Bronsted-Lowry acid donates a proton, and a base accepts it. Simple enough, right? But the Lewis concept, that zooms out a bit. It's all about the transfer of electrons. A Lewis acid accepts a pair of electrons, while a Lewis base donates a pair. The crucial takeaway is that while Bronsted-Lowry focuses on the proton transfer, the Lewis definition broadens the whole scope to the electron pair. And honestly, that's incredibly useful for understanding organic reactions.
To actually see this exchange happen in real time, organic chemists use curved arrow notation. Notice how the arrows trace the literal movement of the electrons. The base uses its electron pair to reach out and grab a proton from the acid. During this tug-of-war, one bond breaks and a new one forms. The acid loses its proton to become a conjugate base, while the base gains a proton to become a conjugate acid. It's just a perfectly balanced microscopic trade.
Moving on to Section 2, measuring strength. Now that we know how protons and electrons are traded, how do we actually keep score?
Well, in water, we measure acid strength using an equilibrium constant called Ka. The more readily a compound donates a proton, the stronger the acid, and the higher that Ka value is going to be. But here's the thing. Dealing with raw Ka values can be a nightmare. The numbers get astronomically small and super messy to work with. So chemists use a brilliant mathematical trick, the pKa value. It's simply the negative logarithm of Ka, and it takes all that terrible, hard-to-read scientific notation and turns it into nice, manageable numbers.
If you take away just one golden rule from this explainer today, make it this. Because of that negative logarithm, the relationship completely flips. A strong acid will have a huge Ka value, but a very low pKa value. So as the Ka gets larger, the pKa gets smaller. Always, always remember, the smaller the pKa number, the stronger the acid. Seriously, burn that into your brain.
Just to put this into perspective and appreciate the crazy scale we're working with here, typical organic acids have Ka values ranging from 10 to the -5th all the way down to 10 to the -50th. That's incomprehensibly small. By converting these to pKa, we get a much friendlier scale of roughly +5 to +15. It makes comparing them so much easier.
All right, Section 3, acid strength factors. We know how to measure strength, but what actually causes it? Why does one molecule easily give up a proton while another holds onto it for dear life?
We've got 5 main structural factors that dictate acidity. The overall structure, electronegativity, hybridization, the inductive effect, and resonance stability. And what's really cool is that they all boil down to one universal truth in chemistry. Nature loves stability. Specifically, anything that stabilizes the resulting conjugate base is going to make your starting acid a whole lot stronger. Let's kick things off with electronegativity. If we compare methanol, which has a pKa of 16, to methane, which has a massive pKa of 43, remember, lower pKa means stronger acid. Methanol is significantly more acidic. Why? Simply because that hydrogen is bonded directly to oxygen. Oxygen is an electronegative powerhouse compared to carbon, so when the proton leaves, the oxygen can handle that left-behind negative charge so much better. It's just more stable.
Next up, hybridization. Check out this progression from an alkane to an alkene to an alkyne. As we shift from an sp3 hybridized carbon down to an sp hybridized carbon, the pKa drops all the way from 43 to 26. What's going on here? Well, increasing the s character of that hybrid orbital basically pulls the electrons tighter and closer to the nucleus. This ramps up the effective electronegativity of the carbon, stabilizing the negative charge on the conjugate base, and boom, you've got a stronger acid.
Now, check out the inductive effect. Standard acetic acid has a pKa of 4.75, but if we swap out one of those hydrogens for a highly electronegative chlorine atom to make chloroacetic acid, the pKa plummets to 2.81. The chlorine acts like a microscopic vacuum cleaner. Right through the chemical bonds, it pulls electron density away from the acidic site. This spreads out the negative charge of the conjugate base, creating massive stability and vastly boosting the acid strength.
Finally, resonance. A standard alcohol loses a proton easily enough, but phenol? Phenol is a much stronger acid than your typical alcohol. When phenol loses its proton to form a phenoxide ion, that negative charge doesn't just sit stuck on the oxygen. It gets shared or delocalized all around that entire benzene ring through resonance. This incredible distribution of charge proves it once again. Stability is king. Section 4. Organic bases. We've thoroughly explored how molecules give up protons. Now, let's flip the script and look at the proton acceptors.
So, we've spent a ton of time on molecules giving away their protons. But what about the other guys? What actually drives a molecule to aggressively pull a proton toward itself? What makes a good acceptor? Enter the amines. Amines are the absolute kings of organic bases because they contain a nitrogen atom. And crucially, that nitrogen holds a lone pair of unshared valence electrons. Think of this lone pair as a perfectly positioned molecular docking bay, just sitting there, waiting to share its electrons and snatch up an incoming positively charged proton.
Which brings us to Section 5, base strength factors. Just like with acids, not all bases are created equal. Let's uncover the mechanics of what makes a base truly strong.
For bases, it really comes down to three main things: the overall structure, hybridization, and resonance. Sounds familiar, right? They're practically the same factors we used for acids. But actually, scratch that. They operate a bit differently here. Let me show you. Here's where things get wild. Think back to our acids. An sp hybridized carbon made for a stronger acid because it held those electrons nice and tight. Well, for bases, it's the exact opposite. An sp3 hybridized nitrogen holds its lone pair less tightly than an sp2 nitrogen. Because those electrons are kind of loose and less restricted, they are way more available to be shared with a proton. So an sp3 hybridized nitrogen actually makes a stronger base. Crazy, right? Resonance pulls a fast one on us here too. You might naturally think, hey, resonance always makes things stronger. But look at amides. The electron pair on the nitrogen in an amide is actually getting pulled away by the adjacent acyl group's resonance. It's an electron withdrawing effect. Because that lone pair is busy participating in the resonance, it's just not available to go grab a proton. As a result, amides are incredibly weak bases in water. So, if you step back and look at the big picture of this explainer, molecular reactions aren't just random chaos. They are entirely driven by the pursuit of electrical stability. Whether it's a molecule donating a proton to disperse a negative charge or a lone pair reaching out to neutralize a positive one, the whole shebang is just about finding balance. We started out looking at static, boring structures, but hopefully you now see the kinetic energy bubbling right beneath the surface. Once you understand this invisible push and pull, you literally have the toolkit to decode the chemical world around you. So the next time you look at a molecular structure, will you just see static lines and letters, or will you see a dynamic, microscopic tug of war waiting to happen? Keep exploring, keep questioning, and I'll catch you in the next explainer.